In this demonstration, I have two balls that look the same, but one is happy and one is sad. First, I'm going to hang the sad ball from this string, bring it back, and release it so it hits the block. The question is, what will happen to the block when the ball hits it? Will it stay upright or will it fall over? The block stayed upright. This is because when the ball hit the block, it was roughly an inelastic collision. The ball and the block became one mass, essentially, with the original momentum of the ball, which is not enough to knock over the block. Now let's repeat the experiment with the happy ball. What will happen when the ball hits the block? Will the block knock over or will it stay upright? This time the block was knocked over. This is because the ball hitting the block was roughly an elastic collision. When the ball bounced off the block, it delivered twice the momentum of its original momentum to the block, which was enough to knock it over.
Here I have two identical tracks. Here I have 4 carts that are free to roll if I place them on the track. All 4 carts have the same mass to start. One end of each cart has a magnet, which I've indicated here with blue tape. The other end has no magnet. When both ends of the carts with magnets are brought close together, the magnets repel each other, preventing direct contact between the carts. If one end of the cart has no magnet, nothing prevents the 2 carts from making direct contact. Here I have 2 identical mass bars, which I will place on top of what I will call the target carts. On this first track, the target cart is turned so that the end without the magnets faces the launch cart, and they can make direct contact with each other. Watch what happens to the first cart when I launch it at the target cart. The launch cart comes to a rest after it hits the target. On this second track, I have turned the cart so that the ends with the magnets face each other, preventing direct contact. Watch what happens to the second cart when I launch it at the target cart. On the second track, the launch cart rebounds after the collision. How does the speed of the 2 target carts compare after the collision? The target cart has a greater speed when the launch cart comes to a rest. The target cart has a greater speed when the launch car rebounds, or both target carts have the same speed after the collision. Let's repeat both collisions, this time watching what happens to both target carts. The target cart has a greater speed when the launch cart rebounds. We can understand this from conservation of momentum. The total momentum of the system before the collision must be the same as the total momentum of the system after the collision. On both tracks, the carts were launched in the forward direction. When the launch cart comes to a rest after the collision on this first track, all of the forward momentum must be transferred to the target cart. When the launched cart rebounds on the second track, it has a backward momentum after the collision. This means that the target cart must have a greater forward momentum so that the total momentum of the 2 carts adds up to the same initial value.
This demonstration involves 2 balls. Now, as you know, if I drop a ball, it returns to a height that's less than the drop height. That's because some energy is lost during the bounce. After all, you hear the bounce, that's sound energy. In addition, the balls will distort a little bit and heat a little bit, and so they don't have as much energy after the bounce as before the bounce, and they don't return to the initial drop height. But now what I'm going to do is a little bit different. I'm going to drop both balls at once, stacked up on top of one another. The question is, when I drop the 2 balls like this, will the small ball bounce back to a height that is less than the drop height, equal to the drop height, or greater than the drop height? Okay, let's try it out, see what happens. I'll try to line them up vertically as best I can. So let's see how it goes. Whoa, all right. Well, clearly the answer is 3. The small ball bounced to a height considerably greater than the initial drop height. Well, how can that happen? How can this ball have so much energy that it goes way up like that? Well, the point is that the large ball collided with the small ball and transferred momentum and energy to the small ball. Energy was still conserved, but a lot of the energy, practically most of the energy actually, that this large ball had got transferred to the small ball. That's why you may have noticed the large ball just stayed put down there. It had sent its energy into the small ball, which then went high. So we have conservation of energy, but a nice transfer of energy from one object to another object. Similar things happen in real life, like for example, when there's a car collision between a large car and a small car. Typically the small car will experience more damage because the large car transfers a lot of its energy into the small car during the collision. Something similar also happens in space. When a star burns out its fuel and begins to collapse to form a supernova, the dense material is near the center of the star. It compacts as far as it can and then rebounds, but less dense material is still coming in and it gets hit and sent out with greater speed. It will hit even less dense material still coming in, send it out with even greater speed. The net result is you can get jets of gas shooting out of a supernova at practically the speed of light. Now I'm going to try to make a little mini supernova here. I'll put one more ball in our system. So we have the more dense material, the less dense material, and the even less dense material. I'll try to line these up and see if we can get a good bounce out of them. All right, try to get them nice and vertical. Okay, so we transferred a lot of energy and momentum. We got a great deal of height. We had sort of our own little mini supernova right here.
So here I have a toy water rocket with an air pump attached to it. Now, this can be fired in two ways. One, with just air, pumping it up just with air, and two, having water in there and then pumping up the air, pressurizing the rocket. The question I have is, will the rocket go further when it uses air as a propellant or when it has the heavy water inside as the propellant? So I'll pump this up 25 times with just the air. I'll let it go. Didn't go anywhere. Now I'll do the same with the water. I'll fill the rocket about a third of the way. and I'll pump it up another 25 times. So as you can see, the rocket went much further. It actually went somewhere compared to the rocket with just the air. Now, why did it go further even though it was heavier? Well, the water has more mass. As it exits the rocket through the exhaust, it transfers a lot more momentum to the rocket than if it was just air pushing against the rocket. Air has very little mass, therefore not a lot of momentum transfer.